Thank you for watching. I'm Masanobu Kunitomo from Kurume University. Today, I'd like to present our recent works on the long-term evolution and dispersal of protoplanetary disks in collaboration with these researchers. First, let me briefly introduce the current understandings of disk evolution. Observationally, the disk lifetime has been constrained. It is thought to be several million years. This figure shows the evolution of the disk fraction of each cluster. Both gas and dust signatures disappear at around 6 million years. Theoretically, this disk lifetime has been examined considering viscous accretion and photoevaporation. The disk is assumed to be turbulent, and the turbulent viscosity drives the angular momentum transport in the radial direction. The origin of the turbulence is thought to be, for example, magnetorotational instability. And the viscosity is parameterized with the alpha parameter. On the other hand, photoevaporation is a thermal disk wind driven by the radiation of the stellar high energy photons. The thermal energy of the heated gas exceeds the gravitational potential in the outer disk, so such gas can flow out from the disk. So far, this framework is thought to be successful, but there still remain unresolved problems. In this talk, I'd like to focus on two questions. How does stellar evolution affect disk evolution? How do disks with weak turbulence disperse? So let me start with the first question. First, I'd like to briefly introduce the evolution of young stars. This figure shows the evolutionary tracks in the HR diagram from 0.5 to 5 solar mass stars. The horizontal axis is effective temperature and the vertical axis is luminosity. And these two gray lines shows the isochrons. And this is 1 million year isochron and this is 10 million year isochron. So on the left, higher mass stars become a main-shaken star within 1 million years. However, one solar mass stars become a main-shaken star at around 40 million years. So higher mass stars evolve more rapidly. And here I'd like to stress two features in the stellar evolution. First, the effective temperature increases with time. Stars are formed on the birth line here, and then evolve along vertical highest track and horizontal Hennier track. And on the Hennier track, stars' stellar effective temperature increases with time. The other is the structure change. Young stars have a convective structure in the Hayashi phase, but intermediate mass stars lose the convective zone and become radiative. So the stellar structure evolves with time. Due to these evolutions, stellar XUV luminosity evolves with time. So far, XUV photons are thought to be emitted by three mechanisms: magnetic activity, accretion shock, and photospheric radiation. For the magnetic activity, stellar structure is important because magnetic activity is originated from the convective motion in the stellar interior. And the spectra of the photospheric radiation depends on the temperature. So these evolutions are important for the XUV luminosity evolution. Since the XUV luminosity determines the photoevaporation rate, we investigate the impact of the stellar evolution on the disk evolution, which has not been studied so far. We solved the 1D diffusion equation considering the viscous accretion and the time-dependent photoevaporation. So we combined photoevaporation model in the literature and XCV luminosity evolution. From the stellar evolution simulation, stellar atmospheric models, and observational or theoretical relations. The settings are shown here. So let's move on to the results. This figure shows the Discoveration around 3 solar mass stars in the radius surface density diagram. In this plot, the evolution looks similar to previous studies. First, accretion dominates and the surface density decreases with time. And once accretion rate decreases down to the photoevaporation rate, a gap opens here. And then both inner disk and outer disk disperse rapidly. However, in this slide, I'd like to stress the important role of the stellar evolution. This figure shows the evolution of the photoevaporation rates. Blue is X-ray, magenta is FUV, and the green line shows the EUV photoevaporation rate. In the previous studies, photoevaporation rate is thought to be assumed to be constant with time. But if we consider stellar evolution, it evolves with time significantly. And interestingly, the dominant mechanism changes from X-rays to FUV. So the decrease of the X-ray photoevaporation is driven by the structure evolution from convective to radiative. The rapid increase of FUV photoevaporation here at around 1 million years is induced by the increase of the stellar effective temperature. So stellar evolution is crucially important for the realistic disk evolution model around intermediate mass stars. I'd like to note that stellar evolution is not so important around low mass stars, which do not evolve rapidly due to the longer Kelvin-Helmholtz timescale. So the photoevaporation rates are almost constant with time, as assumed in the previous studies. We performed Discoveration simulations with varying stellar mass. This figure shows the disk lifetime decreases with stellar mass, which is consistent with observations in these works. For the decreasing disk lifetime, we found that the evolution of FEV luminosity plays an important role in the disk evolution in the intermediate mass stars, higher than about 3 million years. In the magenta region, the photospheric FUV luminosity is high. So higher mass stars disperse mainly due to the FUV photoevaporation. Next, I'd like to talk about the disk evolution with weak turbulence. Recently, both observational and theoretical studies have suggested that disks are not so turbulent. In terms of alpha, it is less than 10⁻³ . ALMA observations have shown that disks are geometrically thin and velocity dispersion is not so large. On the other hand, theoretical studies also have shown that non-ideal MHD effects suppress MRI, and so disks would be MRI inactive. But if we consider only the viscous accretion and the photoevaporation, previous studies have shown that disk lifetime exceeds 10 million years, which is inconsistent with observations. This figure shows the disk lifetime with the viscous alpha parameter, and if we take 10⁻³, the disk lifetime exceeds 10 million years. So here we examine the effects of other physics, magnetic winds and the magnetic accretion. We investigate the discoveration considering viscous accretion, inefficient viscous accretion, MHD accretion, and magnetic disk winds, and photoevaporation. Theoretical studies and MHD simulations have suggested that magnetic force can drive disk winds in addition to the photoevaporation. And magnetic braking drive the accretion. So here we focus only on the discoveration around one thermal star and do not consider celebration. First, I'd like to show the discoveration without photoevaporation. In this figure, we can see that the disk structure is significantly affected by MHD winds and accretion, in particular in the inner region. However, the disk lasts long. In this case, even at 20 million years, the disk remains. This is because MHD winds are driven by using accretion energy. So wind mass loss rate decreases along with the decreasing accretion rate. So we cannot explain the disk lifetime only with the MHD winds and accretion. But we found that disks quickly disperse if we consider both photoevaporation and MHD effects. In this case, the disk lifetime is about 3 million years, which is consistent with observations. This is because, unlike MHD winds, the photoevaporation rate does not decrease in the late phase and therefore drives quick dispersal. Finally, this figure shows the mass loss rates of MHD winds and photoevaporation rates in green and blue lines. We can see that MHD winds dominate in the early phase in the inner region. On the other hand, photoevaporation does in the late phase in the outer disk. So I conclude that these winds are cooperative and both winds should be considered in the realistic disk evolutionary models. So in this talk, I couldn't show the, but we also found that wind-driven accretion should also be considered. So this is a summary of this talk. Thank you very much for watching, and I'm looking forward to talking with you in the online conference.